Welcome back to this module on the MIPS64 instruction set architecture. In this lesson, I will describe the operations supported in MIPS64. I will now give an overview of the MIPS64 instructions. Broadly speaking, there are four classes of instructions: memory access instructions, or loads and stores; ALU operations, that are operations executed on the arithmetic logic unit; control transfer instructions, meaning branches, conditional jumps and jumps, unconditional jumps; and finally floating point instructions. Next, I will discuss each of these classes in turn. First, the memory access instructions, the loads and stores. I will not discuss them all, but just give a few examples. First, the load half-word instruction. In assembly, you write the acronym LH, followed by the destination register, in this case R1, followed by the displacement, in this case 30, and the base register R2. Since a half-word is 2 bytes, this instruction loads 2 bytes, 16 bits, from memory, which I indicated by specifying the interval byte address 30 plus R2 to 31 plus R2. Furthermore, as I mentioned before, the value loaded is sign extended to 64-bit. The second example are the store instructions: store byte, store half-word, store word, and store double word. In this case, the destination, which is a memory location, is specified at the end. There are also MIPS assemblers, however, where you have to specify the destination memory address first. Please look up in the manual of your assembler which is the appropriate technique. The second class of instructions are the arithmetic and logical instruction. First, I want to discuss the difference between the double word add instruction and the double word add unsigned. The double word add, or DAD instruction, performs overflow detection, while the double word add unsigned, DADU, performs no overflow detection. Overflow detection means that if the result is too large to be represented as, in this case, 64-bit 2's complement number, an exception occurs, which in turn means that the address of the instruction is saved in the exception program counter and control is transferred to a special routine of the operating system called an interrupt handler. No overflow detection, on the other hand, means that the program simply continues as if nothing has happened. Which one is applied depends on the programming language. Fortran, for example, which has been used to send rockets to the moon, is very safety critical and therefore defines that overflow should always be detected. So it's rocket science after all. The programming language C, on the other hand, does not care about overflow and defines overflow as a programming error that the programmer should fix. The second instruction in this class that I would like to discuss is the load upper immediate instruction, LUI or LUI. This instruction sets bits 16 to 31 of its destination register to the value specified by the immediate operand. This instruction is inherited from the 32-bit MIPS architecture. It used to set the upper half of a 32-bit register and is kept for backward compatibility. Notice that in my opinion, LUI, LUI, load upper immediate, is not a load instruction. Next, the control flow instructions, branches and jumps. First, the jump instruction. In assembly, you write J for jump and then a label, and this label specifies the instruction that you jump to. The assembler, however, translates this to an instruction address, in this example 1000. This is an instruction address, and since all instructions are 4 bytes, this value 1000 is multiplied by 4 before being used as a byte address offset. Recall from an earlier slide that the instruction address field is a 26-bit field. This multiplied by 4 yields 28 bits, but the program counter PC is 64 bits long. The remaining bits, meaning bits 28 to 63, are taken from the current value of the PC. To be precise, from the current value of the PC plus 4. The second control flow instruction I want to discuss is the jump and link instruction, JAL. This instruction jumps to the specified address, but also saves the address of the next instruction, PC plus 4, in register 31. This instruction is used for function calls and returns. The symbolic name for register 31 is therefore also RA, which stands for return address. The final instruction I want to discuss from this slide is the conditional move if 0. This instruction copies R2 to R1, but only if R3 equals 0. Such conditional or predicated instructions are used to remove branches altogether because branches disturb the normal sequential execution and therefore reduce the execution efficiency. Later in this lesson, specialization, I will return to this issue several times because branches are a big issue. Finally, the floating point instructions. Of course, there are the basic arithmetic floating point instructions: add, subtract, multiply, and divide, each with suffix either .s or .d to denote single or double precision. What is more interesting is that MIPS64 also supports paired single operations. These operations perform 2 operations on each half of a 64-bit floating point register in parallel. They are examples of so-called single instructions, multiple data, or SIMD instructions. We will see more of them in the lessons to come. Next, MIPS also supports multiply add or MAD instruction. These are very common operations in signal processing applications. Finally, branches are implemented slightly different in the floating point data path than in the integer data path. To be precise, there are compare instructions, compare less than, compare less equal, compare if equal, that compare if one floating point register is either less than, less or equal to another floating point registers. These compare instructions set a bit in a special register called the floating point status register that I mentioned before if the result of the operation is true. Thereafter, branch instructions test this bit to see if it is true or false and jump if the condition is fulfilled. Because the first MIPS processor didn't have a floating point unit, but a optional floating point coprocessor, the acronyms of these instructions are BC1T or F, which stand for branch on coprocessor 1, true or false. Finally, there are instructions for converting between single and doubles and for converting between integers and floating points. In C, you would need typecast for that. For example, the last instruction here converts from floating point double to integer word, which in C would mean a typecast. However, before the results of the typecast can be processed further as an integer, it must be moved to the integer register file, for which MIPS provides the move from coprocessor 1 or MFC1 instruction. Similarly, there is a move to coprocessor 1 instruction, which is needed for a typecast from an int to a floating point. This concludes this lesson. Thanks for watching. In the next lesson, I will describe some basic code optimizations that reduce the number of instructions that need to be executed. Hope to see you back.